Welcome to another great video. So now for this example we are focusing on paper from Eastern Cape, still on electromagnetism. So in this particular paper, this was question 9 of the paper, right? So let us check it out. First off, we have a coil with 340 turns, right? So what I usually like to do is I take out my given data or information so that I know what I'm working with. It helps. So now we have that this coil has 340 turns. So N would be 340 turns. And then it has an area of 0.06. Okay, we'll write that. Meter squared. Then it is held with its axis coinciding with the direction of a magnetic field of strength 0.4 Tesla. So now what you will notice there is they've given us two pieces of information. The first one, when they say, or when the statement is saying it coincides, right? Its axis is coinciding with the direction of the magnetic field of strength 0.4 T. Right, so it tells us that basically the direction of the magnetic field, it's in the same, or they are in the same straight line with the normal. So this means that if the normal is like this, right, and the coil is this one, the magnetic field lines are also, if I draw the magnetic field line in that direction, so the angle between the normal and of course the magnetic field lines could be coming there. So the angle between the normal and the magnetic field lines is 0 degrees. That's what it means. That's our normal, that's our magnetic, the coil, right? This is our coil. The blue line is our coil. The black dotted line is our normal, and the red lines are our magnetic field lines. So it would mean that these are in the same straight line as the normal, such that the angle between the normal and the magnetic field lines is simply 0 degrees. So that's what that statement means. Then secondly, we are then given the magnetic field strength. So our theta will be 0 degrees, right? Because of this statement, axis coinciding with the direction of the magnetic field. That's why our theta is 0 degrees. So, and then we know that the magnetic field strength is 0.4 Tesla. So now, in order to induce an EMF in the coil, it is pulled out of the magnetic field in 0.3 seconds. So remember, if it is pulled out of the magnetic field, it means, if you remember our other video, we said it was initially inside a magnetic field and then it is pulled outside. So this means that this value would be our initial value for the magnetic field strength or magnetic field density. And then our final value will simply be 0 Tesla. So if I were to draw an analogous diagram for this situation, I would have something like this, right? So when the coil is outside, which is my purple words, and then when the coil is inside, which is my red. So that red rectangle, I'm just imagine a room where there's magnetic field, and then we place the coil in there, and then we pull it out. As we pull it out, obviously there will be a change in the magnetic flux, which then induces an EMF in the coil. But at some point, the coil will be completely outside this magnetic field. And once it's completely outside the magnetic field, our final value for the magnetic field density becomes 0 Tesla. Right? So we're focusing on the initial and the final. Right? So this is what this statement is saying. So now that's the information we have so far. And then, the time is 0.3 seconds. So we are told that all of this happens in 0.3 seconds. Right, so we have interpreted our question. So now let's start answering the following questions. We've interpreted the statement. Now we can answer the questions that are following. Right? We are asked to state the Faraday's law of electromagnetic induction. Remember, simply put, if we have an induced EMF, so the magnitude of that induced EMF, not if, right? The magnitude of the induced EMF across the ends of the conductor is directly proportional to the rate, keyword, rate of change of the magnetic flux with the conductor. So that's what you would say. Right. So that's our Faraday's law of electromagnetic induction. Now let's go to 9.2. Mention two ways in which the magnitude of the induced EMF can be increased. One, we can try and increase the strength of the magnet. Right, we can try and increase the strength of the magnet, or simply use a stronger magnet. That's another way of putting it. So what that would mean is B would increase, would go high. And then the second option that we have, there's actually a number of options. I think there's about 5 of them. The second option that we have is to then, number 2, it would be to increase the number of turns in the coil. So that's N. Increase the number of turns or loops in the coil. Effectively, what we would be doing, we take N, we increase it higher. So that's what we'll do. So there's quite a number of other options that you can go for. For instance, you can, in this case though, theta is already at its maximum, which is 0 degrees. Usually we will decrease theta, and then if it was at 60, for instance, we would decrease it to 0 degrees, and then at that point we would have increased the induced EMF. Right, or increase the area of the loop, right? That's another way. Or you simply increase the speed at which you are pulling the magnet or the coil. In this case, we are pulling the coil here. Increase the speed at which you are pulling the coil outside of the magnetic field. Right, that's another option. Increase the speed of the coil. So let me just say O. So you increase the speed at which the coil is being pulled out of the magnetic field. So this answer is specific to the context of this question. It's general. You can use it in any situation, in most situations, but I used the last part of it. It's just specific to this question alone. In another question, you would have said maybe increase the speed of the coil or the speed of the magnet, depending on which one is being moved. Okay, so these are the 3 ways in which you can do it, but there's other ways. There are other ways. So these ways are not the only, this list is not exhaustive. So it's not complete. There are other ways in which you can achieve this. So now let's go to 9.3.1. Okay, 9.3.1. Calculate the magnetic flux linkage. So we know that once it's outside the magnetic field, it will have 0 magnetic flux linkage. This is 3 marks, so means they want the magnetic flux linkage when it's inside the magnetic field, right? We know that we can find the magnetic flux linkage using BA cos theta, where B, we were told that it's 0.4. Was it 0.4? Yes. Then our area, we were told is 0.06. Cos our theta is 0 because the axis of the coil coincides with the magnetic field. Right, then we can find our answer, 0.4. I get 0.024 Weber. That's our answer. So this is when the coil is placed inside the magnetic field. So it will have a magnetic flux linkage of 0.024 Weber. So now we are asked to find the magnitude of the induced EMF for 9.3.2. We know that according to Faraday's law, the induced EMF, which is epsilon, is equals to minus the number of turns times the change in the magnetic flux divided by time. Change in magnetic flux divided by time is called the rate of change of the magnetic flux, which is part of the official definition of what Faraday's law states, right? So this is what it would look like. We have the number of turns. We were given time. We are trying to find the magnitude of the induced EMF, but we don't have delta phi. So we know that delta phi, right, is simply final magnetic flux linkage minus the initial one, right? All this over delta T. So if you remember, we said initially this thing will be placed inside the magnetic field, so it will experience 0.4 Tesla. But once it's outside, it will experience 0 Tesla, which means our final magnetic flux linkage is simply the final magnetic field density times the area is the same, times cos theta, the angle is also the same. So the final one is 0. 0 times any number is simply 0, right? Therefore, here we can substitute now. Minus 350. Sorry, where am I getting 350 from? It's 340 times our final is 0 minus, we just calculated the initial, 0.024. This guy is that, right? So, and then this guy is that guy, right? So now what we can do is we can now divide by our time, which is 0.3. Therefore, our answer becomes 340 times 27.2 2 volts. So this is my final EMF. Right, so for this particular question, this is how you would have tackled these 10 marks, right? So yes, that's it for now. Catch you on our next video.